So section 5.1 is going to introduce you to some rules for exponents. Now exponents are really a very friendly way to work with some things. Rather than write a times a times a times a times a, and you're really bored, the shorthand would be to write a to the 5th power. So that's a nice convenience. And let me give you a little bit of vocabulary that surrounds this. So the a here is what's called your base. And it's raised to this power, which is your exponent. And what we're going to do and be careful of in the first handful of examples is understanding what the base is and understanding what the exponent is, because it's going to change, and as it changes it makes a little bit of a difference. So we'll start with problem number 14. We're going to look at the base and the exponent for 3 different types of expressions, although all closely related: x to the 5th, negative x to the 5th, and negative x to the 5th. So in all of these, what's the exponent? What's the exponent for these types? The exponent's 5. 5, 5, and 5. All right, but now let's work on the base of this. What's the base for the first one? X. So it's x to the 5th power, so it would be x times itself 5 times. Let me move over to the last one. What's the base for the last one? Negative x. Thank you. It's the whole thing. So negative x. So if you were to write this out, it'd be negative x times itself 5 times. How about the middle one? What's the base here? Thank you. Just x. Now that negative is not part of this. And the difference is here. So negative x to the 5th, that's the negative of x multiplied by itself 5 times. Whereas negative x to the 5th is negative x times negative x times negative x times negative x, etc. So they mean different things. And the purpose of this early few examples is to make sure you can distinguish between this case and this case. Let's try another one like that. It's problem number 16. Same kind of thing. We're going to try and identify the base and the exponent. This time our expressions are negative 1/3 x to the 6th, negative 1/3 x raised to the 6th, and the negative of negative 1/3 x raised to the 6th. So those are the expressions in 16. I think it's clear what the exponent is going to be, right? The exponent is 6 for all of these. The challenging part then is to figure out, well, what's the base? What part of this is going to get multiplied by itself repeatedly in order to evaluate these expressions? So, Preston, what's the base for the first one, please? X. Good. Let's keep going around. Dwayne, what's the base in the next one? X. Good. It's the whole thing, negative 1/3 x. And let's go into the back corner. Rochelle, what's the base in the last one? Is there a reason that you wouldn't take the x along with that as well? All right, good. So again, it's the same thing, negative 1/3 x. So this negative out in front doesn't really make a difference to the base. It's just negative 1/3 x. Last one like this is problem number 18. Again, we're going to deal with a base and an exponent. So our expressions here are y plus 9 to the 4th, y plus 9 to the 4th, and 8 times y plus 9 to the 4th. So like these previous examples, I think the exponent part is clear. The big job is to figure out, well, what's the base? So the exponent in these is 4. Let's keep going around. LeBaron, what's the base here going to be, please? Yeah, y plus 9. It's this whole thing. Good. Base for the next one, Carrie? 9. Now, notice what a difference it makes. Here, you're multiplying this whole expression by itself 4 times. Here, it's just the 9 multiplied by itself 4 times. How about the last one? Madison, up front? Yeah, y plus 9. Again, this 8 doesn't really affect things. 8 is not part of the base here, so you're not going to multiply 8 by itself 4 times, just the y plus 9. All right. Thank you, ladies.
I got a question.
Please.
For the negative x, would that be negative?
Yeah, interestingly enough, both of these are going to end up to be the same value. But that's only because you have an odd exponent. If you had an even exponent, then it would make a difference. For instance, if I had negative 2 to the 4th and negative 2 to the 4th. Here it does make a difference because in the case of the even exponent, all the negatives are going to cancel each other out. In the case of the odd exponent, you don't have that.
So the bottom one will be negative.
Yeah, the bottom one will be negative. The top one is going to be positive. So it does make a difference in this case. You'll get the same value of the expression in problem number 14, although they do mean different things. Yeah, no, good question, and thank you. Okay, let's try some more, kind of following up on that. These are going kind of in the opposite direction. Instead of looking at the base and the exponent, well, I guess it's the same kind of stuff. So we've got negative 5u times negative 5u times negative 5u times negative 5u. One last one, negative 5u. I want to write that with exponents. Likewise with problem number 22. Negative 5 of u times u times u. And I'm going to add a bonus one in here, u as well. I think the book only has 3. I wanted to do 4. So the goal is to see if you can't write both of these with exponents. Let's go all the way back to McKenna. Like that? Ah, there we go. In parentheses. Perfect. So it's the whole thing raised to the 5th power. So the negative 5u have to be in parentheses. Cool. All right. Let's continue. Problem number 22. Madison? All right. Let me give you 2 different options here. Negative 5u to the 4th and negative 5u to the 4th. So A or B. Which one? A. Good. So in this case, it's just the u that's repeated. So I don't want that. Here, u is the base of this. It has nothing to do with the negative 5. It doesn't apply to the negative 5 at all. All right, thanks, ladies. You may remember back a while ago, we talked about that Christmas card example that I gave, right? Remember that I talked about this one? Yeah. All right. So the difference here, I used to get a Christmas catalog that wanted to sell me these T-shirts that said this, and they're trying to say ho ho ho. What it says is who. Now what it really should say would be ho to the 3rd power, and that would be your ho ho ho. All right. Let's try and figure out some of these rules for exponents. And it's going to start with our product rule for exponents. Rules for exponents. So we'll start with this one, a to the m times a to the n. And actually, you're going to help me figure this one out. We're going to figure out together what this rule should be. So I'll leave a little space there. We're going to figure it out with our own example. And you can do this kind of stuff for yourself. If on a test you're like all of a sudden really flustered and you can't figure out, well, gee, what's that rule? There's nothing that stops you from doing something simple like this. Let's take a to the second times a to the third. Now what does it mean to have a to the second? That's a times itself twice. And then a times a times a for a cubed. All right. How many a's do I have all together? 5 of them. So that's a to the fifth. But looking back, can anyone see a shortcut to go from here to here? Add the exponents, right? It's exactly what you're going to do. Add the exponents. So that's going to give me a to the m plus n is your shortcut, or better yet, your rule for working with the product of two things with the same base. You're going to add their exponents. So let's do some practice with this one. That'll start with problem number 28. Three to the fourth times 3 to the sixth. And let's also throw in problem number 30 as well. A to the third times a to the third times a to the fifth. Let's see. Where's that? Shane, maybe you can work on the problem 28 for us. What would 3 to the 10th power? Perfect. What I'm very happy you didn't do is you didn't multiply 3 by 3 and get 9. The only thing you're going to do in these is add the exponents. So 3 to the 10th power. Great. We're going to leave it like that. If you end up with something that's a 2 or 3 digit number, 2 or 3 digit number I probably want, but I mean beyond that, I really don't want big numbers. I want to see that you know your rules for exponents. Cool. Autumn, let's move up to problem number 30. Good. 3 plus 3 plus 5 is a to the 11th power. Well done. Can I apply this rule to something like problem number 30? T plus 1 to the fifth times t plus 1 to the third. Does that work there? Sure. Liam, what do I get when I multiply these together then? Yeah, t plus 1 to the eighth. Again, adding the exponents. Let me give you two more from this part of this, applying to this rule. Problems 34, u to the third, v to the fifth, times u to the fourth, v to the fifth again. And kind of a nice friendly one here, problem number 36, y to the ninth times y to the second. Now, a little bit of a hint here with problem 34, if you wanted to, because all these things are being multiplied, multiplication is what they call commutative. You can change the order here. So it's going to be u to the third times u to the fourth times v to the fifth times v to the fifth. So you can reorder those if you want or need. Okay. Austin, how about problem number 34 here? How could I rewrite that? Good. Can I go any farther? Can I write something to the 17th power? No. The bases aren't the same, so you're kind of stuck there. Derek, how about problem 36? Yeah, y to the 11th. Thanks, gentlemen. Let's learn a different rule. Let's figure out the nuances of something else. Are you okay with our rule for multiplying things with the same base? You add the exponents. That one I'm pretty good at. Let's see if we can't figure out what happens with division. In other words, if I have a to the m divided by a to the n, now what's going to happen? What am I going to get? Well, it's a good question. Let's figure it out. We're going to do it the same way we did with the last one, with a small example. So let's start with a to the 5th over a to the 3rd. And what I'll do here is I'm going to remember what a to the 5th means. A to the 5th means a multiplied by itself 5 times. And likewise for a to the 3rd. Okay. But having expanded it like this, is there any simplification I can do? Well, I cancel out one of the a's there. And cancel out another one. And another one. Now I've kind of run out of a's in the denominator. What am I left with? A times a, or better yet, a squared. Now, I think I heard some of you guys anticipating me on this. What's the shortcut to go from here to here? Subtract the exponents. Good. So in general, it's going to be a to the m minus n. So that's another rule that you should know, is how to deal with the difference, or excuse me, the quotient of these things is subtract the exponents. By the way, don't cancel out the a's. Don't write, oh, a cancels and get 1 to the m minus n power. In fact, that brings to mind something kind of funny here. And let me see if I can't find that real quick.